This is Lab 2, Charge Tapes Revisited by iishim Oberoi. Like Lab 1, the purpose of this lab is to create charged pieces of tape, observe their interactions, and calculate approximate excess charge. The purpose of revisiting this lab, however, is to create a more realistic model and observe how this model affects our outcomes as compared to the simplified model we used in Lab 1. Some of the physics principles we will use in this lab are the electric field, force electric, force gravitational, and electric field of a rod, and that's given by its general equation in this slide. Our main results were that the original charge was approximately negative 2.259 e to the negative 8 coulombs, and our new charge was around negative 4 e to negative 8 coulombs. The biggest difference in Lab 2 is that we're using line charge models instead of a point charge. This means we're taking tape A and B and turning them into line charges and subdividing them into small pieces, and from there we can calculate the electric field on each part of tape B by each part of tape A. And of course, we can calculate force electric and force gravity on tape B afterwards. Our system is the top tape, tape B, and surrounding is everything else, including tape A. Our two main assumptions is that we're ignoring air resistance and the charges are evenly distributed across the tapes. To better explain my model, I'll just briefly go over our observations and results from the Lab 1 experiment. To start off, we have a base tape that's stuck onto a table and is used to charge other pieces of tape that are assumed to be neutral. After charging, the tapes must be negative because they were repelled by a negatively charged pen and attracted to neutral matter. Then we created two charged tapes and were able to float tape B above tape A using its repulsion. Then, using the point charge model and Newton's second law, we were able to calculate a rough estimate for what the charge should be on each tape. For the coding section of this lab, I started off by defining my constants, which was m, which is mass, big Q, which is the charge that we derived from the point charge calculations, and distance in meters. Then I went on to define the electric field equation, starting with defining little q, r, which is just the charge particle position subtracted from the observation location, and from there I could just write the formula for the electric field. Moving on to the image on the right, on lines 79 and 80, I edited some values, so I set the top tape to be at the origin, the bottom tape to be at a y value of negative distance, and then for both of them I set their n number to be 14. Starting with the image on the bottom left, I set my E scale to 1 e to the negative 5.5, my FE scale to 100, and then I set FE on DQ top by DQ bottom equal to DE at DQ top by DQ bottom times DQ top dot charge. And then in line 123 and 124, you can ignore that. That was just me testing the code on those hashtags. And then on line 127, E at DQ top arrow dot axis, I set that to E scale times E at top DQ, or E at DQ top. In the actual visualization of this code, we see each green arrow is the electric field produced on the red segments by the blue segments. The gray arrow, which is a little bit hidden, is the electric force, and the yellow arrow is the gravitational force. Logically, we know that the gravitational and electric force should be equal, but obviously they're not. And this is most likely due to the fact that we used a charge value given to us by the point charge model that we used in Lab 1. After a little bit of trial and error, on the image on the right you can see I changed my Q value to 4e to the negative 8, which is a little bit under double what our original Q value was. And now on the image on the left you can see that our magnitude of electric force and magnitude of gravitational force are almost equal, as also given by the arrows. To go over this one more time, the original magnitude we calculated using our point charge assumption in the first lab was that it was negative 2.259 e to the negative 8 coulombs. But now, using our new line charge model, we found that negative 4 e to the negative 8 coulombs gives us a roughly equal force electric to force gravity. Now, these are under the assumptions that there's no air resistance and that the tapes have uniform distribution of charge. To wrap this experiment up, if we had modeled these tapes as point charges as we did in Lab 1, first off, we wouldn't have had such complex calculations. But also, the Q value, or the charge of each tape, would be smaller than it is if we used the line charge model, which we saw in this lab. This is because the line charge is simply more realistic. And why is this? Well, the tapes aren't infinitesimally small points in space, like the point charge model assumes. They are a distributed line, or in this case, we assume they're a distributed line of charge, where each infinitesimally small chunk of that line exerts a force on each infinitesimally small chunk of the other line. Now, this causes a compounding effect of electric forces, which means that our Q value should be greater than that of the point charge, which we saw in this lab. And that's why this line charge model is more realistic.